So in this video there are three integrals, all of which are made up, where the integrand is made up of proper rational functions, and what I want you to do is to calculate them, and then on the next slide the answers are stated, and then if you have any problems with any of them you can move on and look at the rest of the video to see how they should be calculated. So what I suggest you do now is pause the video, write down the integrals, calculate them, and then and only then move on to the next slide. So here we are, here are the integrals and here are the answers. And the first one I've written in two different ways, showing it can be simplified using the rules for logarithms. Here I've used the rules for logarithms to simplify the result. And if you have got all of these three results, well done. And if you have any problems or any queries about any of them, you can move on to look at the rest of the video to see how each of these integrals should be calculated. So now I'll move on to the next slide and calculate the first integral. So when we look at this integral, we see that it is a rational function. It's a polynomial over a polynomial, and that the highest power in the numerator is lower than the highest power in the denominator. And we look at this and we realize that it is not factorized, and by the fundamental theorem of algebra we know that this can be factorized or it's an irreducible quadratic. So let's see which it is. So to do this, let's just recognize that x squared plus 3x plus 2, it's going to be x times x here, and here it's going to be 2 times 1, and 2 plus 1 is 3. So this means that we can rewrite our integral as the integral of x plus 2 times x plus 1 in the denominator. So we now look at the integrand, and we want to write a partial fraction decomposition of it. So our partial fraction decomposition is going to be x plus 3 over x plus 2 times x plus 1 is going to be a over x plus 2 plus b over x plus 1, where a and b are both unknown constants. And what we now do is we put this on a common denominator, and the common denominator is by construction going to be the same as the denominator on the left hand side, the denominator in the original integrand. So our denominator is going to be x plus 2 times x plus 1. And what we're going to require is that the numerator here and the numerator here, once we put this on a common denominator, must be the same. So we require that x plus 3 is going to be, well, over x plus 2, x plus 1 is going to be a times x plus 1 plus b times x plus 2 all over x plus 2 times x plus 1. So we have the same denominator, the numerators must be the same, and now we say that we equate coefficients of powers of x. Because if the numerators are to be the same for all possible values of x, as you change x, these change in different ways, and so therefore we have to have the same coefficients here. So the coefficient for x to the power 1 on the left hand side is 1, and on the right hand side you get it a times x and you get b times x. So we're going to get a plus b. We also have the coefficient of the constant term, x to the power 0, and on the left hand side we have 3, and on the right hand side we have a times 1, and we have also b times 2. So this is going to give us a plus 2b. So now we have two equations in two unknowns and we want to solve them. And I think the easiest way is just to look at this and realise that the a's are exactly the same. Here in this equation it's the same as this equation except we've added a b to it, and we've gone up here from 1 to 3, so b must therefore be equal to 2. So the solution is b is equal to 2. And if we look at this equation here, say, if b is 2, a has got to be minus 1, so that a plus b would be 1. So we have a is equal to minus 1. And let's just check this carefully by looking at the other equation. So in the other equation we have a, which is minus 1, plus 2b, 2 times 2 is 4, minus 1 plus 4 is 3, and that's exactly what we have here. So that works. So we should always check solutions to sets of simultaneous equations, and we now know with confidence that this is the right answer. So therefore our original integral, and let me for brevity write at the top here, let me give this integral a name, let me call it I. We know that we can write I as the integral of a over x plus 2, but a is minus 1, so it's the integral of minus 1 over x plus 2 plus 2 for b times 1 over x plus 1. Both of these terms, when we integrate them, are going to give logarithms. This is the logarithm of x plus 2 with a minus sign in front of it. So we get, I'll put some space here, minus the logarithm of x plus 2. Easy to check, differentiate this, you're going to get 1 over x plus 2 times the derivative of x plus 2, which is 1. So we will get exactly this. And then from here we're going to get plus 2 times the logarithm of x plus 1. And if we want to, we can now put these over one logarithm by combining them together. So the 2 comes, and this can be simplified from the rules for logarithms. So what we do is we just take the 2 up to here to square the argument, and we bring this, because it's got a minus 1, into the denominator. So we get the logarithm of the modulus of x plus 1 all squared divided by x plus 2, close the modulus. And this is our initial integral, the integral of x plus 3 over x squared plus 3x plus 2 integrated with respect to x. And that is our final result, written either in this way or in this way. And the result is of course valid up to an overall integration constant. So with that I'll move on to the next slide and the second integral. So our second integral is again a proper rational function in the integrand, and if we look at the denominator we can easily factorize it by pulling out a common factor of x squared. So what we have is that our integral is equal to the integral of 1 minus x in the numerator over x squared times x squared plus 1, and the final factor here, x squared plus 1, is an irreducible quadratic. So we want to write out our partial fraction decomposition for this. So the partial fraction decomposition is the following. We want to write 1 minus x over x squared plus 1 as. So we have x squared in the bottom. That means we definitely have to have a value of some number over x squared in our decomposition here. But we could also have a subleading term, something over x. We don't know whether that's there or not, so we have to assume it could be there. So we can write down a over x plus b over x squared. And as said, we know that b isn't 0. We don't know if a isn't 0, but it might not be 0, and if we don't write it down, we have to ask ourselves, well, do you feel lucky today that that is definitely 0? So assume it's there. Then the other term we have involves the irreducible quadratic term in the denominator. So that's x squared plus 1. And what we do now is we write in the numerator all possible terms which give us proper rational functions. And because this has got an x squared here, we're allowed to have a term that is linear in x. So I'm going to write this as cx plus d. And now we've completed our partial fraction decomposition, and what we have to do is to calculate a, b, c and d by putting the terms on the right hand side over a common denominator, which is this denominator here, and then saying that the numerators must be the same power by power in x. So let's put these over our common denominator, and what we have is that the common denominator is x squared plus 1, and a is going to be multiplied by x times x squared plus 1, b is multiplied by x squared plus 1, cx plus d are going to be multiplied by x squared, so that gives cx cubed plus dx squared. And this is just this over our common denominator, which is the original denominator. So we want this and this to be the same, so let's just write that out again, 1 minus x over x squared plus 1. So that tells us that the numerators have got to be the same, so now we can equate powers of x. So let's equate powers of x in the numerators. So the highest power of x that we see over here is x cubed, that we can get from here and here. So the coefficient of x cubed, on the left hand side there aren't any, so that's easy, it's 0, and on the right hand side it's a from x times x squared times a, and it's also c, so it's a plus c. Moving down, the next power down is x squared. Again, there are none on the left hand side. On the right hand side there are none with a because we've got x cubed plus x, but with b there is an x squared term, and with d there is an x squared term. So we write b plus d. For x to the power of 1, there is now something on the left hand side. We have minus 1 here. On the right hand side we have an a when the x multiplies the 1. We don't have any b's, we don't have any c's, and we don't have any d's. So we have that we just have an a here, and that's very nice because it tells us immediately the value of a. And then finally we have the constant term. The constant term on the left hand side is plus 1, and that's here. And on the right hand side there are no constants with a. With b there is a constant, so we have b from b times 1, and there are no constants with c and d, so this is also very nice. It tells us that b is equal to 1. So we've got a result for a result for b, and then from the other two equations we can read off what c and d are. A plus c is 0, a is minus 1, so this tells us that c is equal to plus 1. B plus d is 0, b is 1, so therefore d is minus 1. So our result for the partial fraction decomposition is that we have minus 1 over x, b is plus 1, so we have plus 1 over x squared. I'm just substituting these four values into this original equation, a, b, and then we go to cx plus d. C is 1, d is minus 1, so we have plus x minus 1 over x squared plus 1. So this is our partial fraction decomposition, and this tells us therefore that our integral I is going to be the integral of minus 1 over x plus 1 over x squared plus x over x squared plus 1 minus 1 over x squared plus 1, all integrated with respect to x. So all I've done here is I've taken the values here, put them into here, into our integrand, and what I've done is I've broken up this into the sum of two terms because they're going to be integrated in different ways. So looking at this, we can write down our final result. So we see that therefore the integral 1 minus x over x to the fourth plus x squared, integrated with respect to x, is going to be minus the integral of 1 over x, and that is minus log x. We also have the integral of 1 over x squared, and that is minus 1 over x. If you differentiate that, you get plus 1 over x squared. The next term is the integral of x over x squared plus 1, and that is going to be the logarithm of x squared plus 1. And now if I differentiate that, I'm going to get 1 over x squared plus 1, which is good. Multiply from the chain rule by the derivative of x squared plus 1, that's 2x. The x is good, I don't want the 2, so I put a factor of a half in front. And then finally we have minus the integral of 1 over x squared plus 1, and that's a standard result. This is therefore minus arctan of x, plus, if you wish, an integration constant. And that is our final result. You can, if you wish, as I did on the second slide, combine these two logarithm terms together. But I will stop this here for this one. So the key structures that we did here were to realize that we could factorize our integrand rather simply. We also realized that x squared is itself not an irreducible quadratic because it factorizes into x times x. And then we can write this as a over x plus b over x squared plus cx plus d over x squared plus 1. Those are all the possible proper rational functions that can generate this denominator here and these types of proper rational functions. And then what we did was we just solved, put these things in a common denominator, solved the equations and calculated what the coefficients are, and then we just carried out the integrals. So with that, I'll move on to the next integral. So in this final integral in this quiz video, and I should add the measure, what we want to do is to first of all write down the partial fraction decomposition. We also notice here there's a factor of x to the fourth, so let's just check that this is proper. Well, the highest power here is x to the fourth. On the bottom though, if I expand that, I will get x squared squared, so I get x to the fourth times x to the fifth overall, so this is a proper rational function. So let's immediately therefore go straight through to writing down the partial fraction decomposition. So the partial fraction decomposition is going to be 1 plus 2x plus x to the fourth all over x minus 1 times x squared plus 1 all squared is going to be a over x minus 1 plus bx plus c over x squared plus 1 plus dx plus e over x squared plus 1 all squared. And we know that at least one of these two coefficients must be non-zero to give us this x squared plus 1 squared in our original denominator. And this subleading term, we don't know if those coefficients are non-zero, but we have to assume it's potentially there, because if not, we are assuming that these are zero with no evidence. So now, as before, we put these terms all on a common denominator. The common denominator is the original denominator. So we have x minus 1 times x squared plus 1 all squared. So we have a times, and now we will multiply this by x squared plus 1 all squared, so that cancels with that, and we're left with a over x minus 1. What I'm going to do now, just to save a bit of space, is I'm just going to immediately expand the x squared plus 1 squared. So I have a times, and x squared plus 1 all squared is x to the fourth plus 2x squared plus 1. And then we have bx plus c times x minus 1 times x squared plus 1. And finally we have dx plus e times x minus 1. So now what we have to do is, on this side we have to multiply these terms out and equate the powers to the powers on this side. So I'm going to immediately ignore the denominators because they are by construction the same, and just look at the numerators. So let's have a go at that. So this tells us that 1 plus 2x plus x to the fourth is going to be equal to a times x to the fourth plus 2x squared plus 1 plus. Now we can just multiply these terms out, but let's do it slowly. We have bx plus c times, now x minus 1 times x squared plus 1 is x cubed plus x minus x squared minus 1. So that is x cubed minus x squared plus x minus 1. And then the dx plus e we can multiply out, so we're going to get plus d times x squared minus x plus e times x minus 1. So now we can equate the coefficients of x. So the highest power of x on the right hand side, so on the left hand side, is x to the fourth, and here as well we have an x to the fourth here. Here x times x cubed is x to the fourth. That is the highest power. So we're going to equate coefficients, and for x to the fourth we have 1 is equal to a from here. We also have b here, x times x cubed, so that's plus b, and there are no further x to the fourth powers. For x cubed, on the left hand side we have 0, and on the right hand side there are no terms with x cubed from a. With b there is an x times a minus x squared, so we have minus b. We have plus c from here, c times x cubed, and there are no terms here or here. So this equation is already quite nice. It tells us therefore that b equals c. We also have an x squared coefficient. On the left hand side we don't have any, but on the right hand side we have 2a from here, a times 2x squared. We have b, x times x is x squared, so we have plus b, For c, we have minus c, which comes from the c multiplying the minus x squared. And now d enters the game because we have plus d. But bear in mind that we know that b is equal to c, so b minus c actually is going to vanish. Let's now look at the coefficient of x to the power 1, and on the left hand side we have two of them, and on the right hand side we have nothing with a, but with b we have x times minus 1, so that's minus b, and with c we have c times plus 1, so we get plus c. And minus b plus c, again, we know that vanishes. But there are other terms involving 1 power of x, and they occur here from minus d and plus e. So it's minus d plus e. And finally we have the constant terms, x to the naught. On the left hand side we have one of these such terms, and on the right hand side we have a from here, a times 1. We don't have any with b because it's multiplied by x, but we have c times minus 1, so that is minus c. We don't have any from d, but we have a minus e. So now we have 5 equations for 5 unknowns, a, b, c, d and e. We know already that b is equal to c, which is very useful. It's cancelled here and here. And in this equation, this final equation, we can use the fact that b is equal to c and write down here that we have 1 is equal to a minus b minus e if we want to get rid of c immediately. So now we have 4 equations for 4 unknowns. We have this equation, we have this equation, we have this equation, and we have this equation, and the 4 unknowns are a, b, d and e. So let's write out these equations explicitly so as to see what we're doing. So we have a plus b is equal to 1. We have 2a plus d is equal to 0, so that tells us d is minus 2a. We have 2 from down here is equal to minus d plus e, so on here we're going to have 2 and minus d plus e, but d is minus 2a, so minus d is 2a, so we have 2a plus e, so that's just this equation here rewritten in terms of a and e. I'm trying to get rid of writing d, and then we have our final equation that 1 is a minus b minus e, so let's just write that straight down. So a minus b minus e is equal to 1. So we've got now 3 unknowns, a, b and e, and we know that d is going to be minus 2a. So let's call this equation 1, we'll call this equation 2, and this one equation 3. So if we look at equation 2, it only involves a and e, so it's quite natural to try to combine equations 1 and 3 to get rid of b, and the easy way to do that is just to add 1 and 3 together, because here we've got a plus b and here we've got a minus b, so the b's will cancel. So adding 1 and 3 is going to give us 2a, the b's cancel, and we have minus e, and this is going to be equal to 1 plus 1, so that's going to be equal to 2. And this is equation 4 from 1 plus 3. So now if we compare equation 4 and equation 2, we see here we have 2a plus e is 2, here we have 2a minus e is also 2, so the conclusion has to be that e is equal to 0 and a is equal to 1. So therefore e equals 0, a equals 1. Now we also know from looking at equation 1 that a plus b is 1, so if 1 plus b is 1, b has to be 0. So therefore b is 0. B is equal to c, so c is also equal to 0. Remember, earlier we showed b is equal to c. So, we've also got down here that 2 is equal to minus d plus e. If e is equal to 0, as we've just shown, d is minus 2. So d is minus 2. So now we have solved our set of simultaneous equations, and we have all 5 of the coefficients, and what we see is that only 2 of the coefficients are non-zero. This coefficient here and this coefficient here. So now what I want to do is to make some room, and then having done that, insert these coefficients into this, and then put this here in the place of the original integrand, so we're just rewriting our integrand in this way, and then carry out the integrals. So let me just pause and make some room. So what we've seen is that our integral I is equal to the integral of a over x minus 1, but a is 1 over x minus 1. And then we have b and c here, but we've seen that b and c both vanish. We have d times x, and d is minus 2, so we have minus 2x over x squared plus 1 squared. And e also vanishes, this term, so that's it. So this is our integral. The first term is just a logarithm, so this is the logarithm of x minus 1, and the second term is simple if we realize, although it looks complicated, if we realize that 2x is the derivative of x squared plus 1, then this tells us that this is going to be something like 1 over x squared plus 1 to the power 1. So we just added 1 to the power here. So let's just check whether there should be some number here. If I differentiate 1 over x squared plus 1, I'm going to get a minus sign because it's x squared plus 1 to the power of minus 1. I'll bring that minus sign down. That's good, I have that there. I will decrease the power by 1, so I would have x squared plus 1 to the minus 2, and that's exactly what I have here. And I would then, from the chain rule, multiply by the derivative of x squared plus 1, which is 2x, and I have a 2x factor there. So that's lovely. So I'm just going to put plus 1 over there, and I know, I've just checked, that the derivative of this is exactly this term. So up to an integration constant, this is our result for the integral. So what we did here was we wrote out the partial fraction decomposition allowing all possible structures, and then we had a set of 5 simultaneous equations and 5 unknowns, and when we tried to work through that we found that only 2 of the coefficients were non-zero. The first integral was straightforward. The second one, you might think that you have to do some sort of tangent substitution or simple substitution, but actually I think it's an integral that can be done by inspection. And if you practice doing things like that, it makes life quite a lot easier. Okay, so with that I will stop this video.